We are Team 7, and this is our semester-long project, a motorized time-lapse rover.
Our product is a motorized time-lapse slider rover that introduces a real-time movement into time-lapse photography shots. It's made of 20 different 3D printed pieces into one compiled final product. It is made for and intended for amateur photographers who may not be able to afford expensive equipment such as sliders that can do this. That costs upwards of $600.
Now we're going to move on to talking about our final product design. All of these models were modeled in Creo as well as assembled in Creo. This assembly allowed us to place all of our components and make sure that they fit mostly ahead of time, so we didn't have to print things twice and redo dimensions. Now we're going to move on to talking about individual components and how they work and affect our build. Alright, so one of the first problems we had is that the Prusa printers that we have in our makerspace are only 21 centimeters by 21 centimeters. This meant that we needed to divide our base into two components, one to hold the steering and one to hold everything else. We used slots to hold most of the things that were determined on placement. This allowed us to adjust things as we went, and we included a bunch of holes in our base as well that let us take things off and put them back on as we wished. This introduced a lot of modularity to our design. Now we'll talk about our steering geometry. So a big part of this design was not only moving our rover in a straight line, but curving it as well. We accomplished this using Ackerman's steering geometry, which ensures that our wheels stay in the same position that they need to be in order not to rub or stop the car. This geometry composes of three main parts mostly. This is the A-arm, which the wheel connects to, and this part right here pivots within the A-arm mount. And in order to keep these A-arms moving at the same speed and in the same location, we're using a steering linkage. This allowed us to keep it pretty consistent, and in order to mount it, we just used some 3mm bolts and nuts that allowed us to keep the height as wherever we wanted.
So for the gears, we originally had a normal ratio of just a gear to another gear, but we saw that that would have been way too big, so we ended up going with a compound gear ratio with a 36 to 324 ratio. These were grab CAD gears. We took them offline because they were going to be much more difficult to manually create, and we 3D printed the gears. We placed them just so perfectly that they fit without any sort of rub or any sort of give. We also did the vice grip in two pieces, all 3D printed. In the back here, there's springs that hold it together for all different types of phones. I tried it on several different types of phones. An iPhone 5C could fit in it, as well as up to an iPhone 7 Plus.
So for the wheels, we had two different designs. For the rear wheels, they were just held in place for maximum friction. The front wheels had bearings in them, which were attached to the steering bar, which allows them to turn left or right, because it was an important aspect of our design for it to turn and curve. And then for the design overall, they were both 86 millimeters in diameter and 20 millimeters in width.
So to run our rover, we have a simple electronic circuit here that consists of 5 pieces, an Arduino Uno, a 12-volt power supply, an L298N motor driver, an integrated push button, and a 100 kilo ohm potentiometer. These connected in this specific manner will allow for 5 volts of the 12-volt battery supply to be pushed in the Arduino to run the code for the motor. Then from that output, you can then run to the L298N driver that will bump the 12 volts back into the motor to be able for it to run. As well as for speed control without messing with the coding for the motor and the Arduino, we simply placed a 100 kilo ohm potentiometer, and with the screw on the side you can reduce the resistance or raise it and you can change the speed.
So now we're into the design calculations. So some of the most key important details of this were the gears and how they're placed on the body. So we start with the gear ratio. Now earlier I talked about a compound gear ratio. To find that we have to add up the two smaller gears and the two larger gears. To find the smaller gears, we took the gear ratio of 36 and we split it into two parts. Now these gears can't be smaller than 6, or they had to be bigger than 5, because printing that is just way too small. So we ended up just going with 2 6s, because it equals 36. For the 324, we also have to have 2 gears. To make it simple, we just found the square root of 324 and made 18 our large gears. Now for RPM, we use this equation to equate the RPM of the motor to the RPM of the largest gear. We use RPM of 2 for the motor because that is the fastest speed that we would ever be running it. We get through here, and then you end up with 0.222 RPM. So now we have to get into average velocity to find out how fast this thing is going. To find that, we have to first find the circumference. We use the biggest wheel as the diameter, which is 86 millimeters. Divide that by 2, you get 43 for the radius. You end up with a circumference of 270.04 millimeters. And then to find average velocity, we multiply the RPM from the last slide as well with the circumference of this slide, and we get 59.95 millimeters per minute of a speed. Now we also have to talk about placement, how we put it on here. So for quick mention, because this will come in handy, the radii of the 6T and the 18 tooth gears are 10.5 and 43 millimeters respectively. So to find out their placement from each other, I essentially just subtracted the radius of one gear by 5 millimeters and have that be axle to axle length.
So for our team functioning, our team was able to cooperate well despite like schedule conflicts, and we communicated very well, which allowed us to find out times when we were all available to meet up and work on a project. Even though from the beginning to the end, our ideas and design concepts, we were able to talk them and share them with each other so we could incorporate them all into the design. So everybody's idea was into the product eventually. And the team was unable to meet up as frequently as we wanted to because scheduling and work and everything, so it was hard, but near the end we were able to meet up more frequently to finish the product and get it done.
So here's the presentation for our final product. I just simply need to plug in one wire to turn on the Arduino. You can see that light, and then press the button on the motor controller. The motors are now running, and you should be able to see that wheel is moving very slowly as intended. Like we said in the design calculations, it's only 53 millimeters per minute, and on the bottom you can see that the gears are moving from the motor to then move the wheels. Another design aspect was the steering, and this Ackerman steering geometry does work both left and right. It can be set during the entire time lapse to produce an angle. From here, we will show some time lapses that we filmed a few days ago and show that it's working.